Thank you, Marco, and thank you for having me. As Marco said, I'm going to present FIG, the Finite Improbability Generator. This is a statistical model checker that we have been developing in my university, originally in Argentina, then the Netherlands, now here in Italy. So what is a statistical model checker? Essentially, we perform model checking by a simulation. This requires that the models that you are going to analyze are fully stochastic, so there should be no non-determinism. Let me give you a very tiny example, a buffer where packages arrive with a certain rate. Okay, so this is exponential, and they are served also at a certain rate. So we have a model, a modeling language to describe these kind of models, where the arrival times, which are stochastic, are explicit variables called clocks. Here you see one. And then the server has another clock that is also exponential. This is exponential only because this is a very traditional example from the literature, but in principle, statistical model checking can, and simulation in general, can do with non-Markovian distributions as well, as I'm going to show later. Okay. And in particular, from this kind of models, we would like to study different behavior. What do I mean by behavior? Well, let's say, for instance, the transient property. What is the probability of satisfying certain conditions until a goal is reached? Or the steady state behavior of the system, which for simulation is a bit weighty in its definition, but let's just say that the proportion of time that a property is being fulfilled by the system, okay? Now, in systems such as small as this one, actually statistical model checking is overkill. I mean, there's even analytic solutions for this kind of single buffer system, but you don't have to go much further to stop having analytic solution, just put another queue in tandem, and that's it. Now you have to resort to another kind of solutions for these systems to study transient and steady state properties. For instance, you could do numerical approximations like in model checking, the standard model checking, or simulation analysis like in statistical model checking. Now, for the sake of argument, in this system, which is still Markovian, you could use model checking, but I'm going to use statistical model checking. Remember that in these cases, what you get is not a precise probability, but rather an estimate, a probabilistic estimate on which you have statistical guarantees on its correctness. Those guarantees are essentially the confidence, which more or less defines the likelihood of your interval containing the true probability value. That's not the correct definition, but it gives more or less the idea of what the confidence is. You want high confidence, so a high chance of containing the right value. And this interval that you are going to provide has a certain width. It's a probabilistic interval for these properties, so it's between 0 and 1. So you want it to be as narrow as possible, because otherwise I will give you always the interval 0, 1, and that always contains the true value. That is not very informative, okay? Now, if you are going to do simulation analysis here, the problem arises when the property that you want to study, like here, the probability of having an overflow in the second queue, is rare. That happens here if this second server is faster than the first one, because any package that is served here goes away quickly and doesn't have time here to accumulate and generate an overflow. Okay, so if you want to do simulation analysis in these kind of systems, you're going to spend a very long time simulating to get a useful confidence interval, a narrow one which contains the true probability value. So that's what FIG was created for, to analyze these kind of systems using a technique called red event simulation, which is essentially Monte Carlo simulation, a little bit smarter. There are different ways to perform this red event simulation. The one that FIG focuses on is called importance splitting. I am not going to mention much about the details of that, because the idea of FIG is that we are going to automate what red event simulation means and what importance splitting means, so the user gets a very similar experience to a crude Monte Carlo simulation. Let me start with a demo of the tool. This is going to be a functional demonstration, so you're going to see its capabilities. It has a command line interface because we all hate GUIs, we all love CLIs. FIG is a Linux tool, so this is a Linux shell. I'm going to be using this alias that I created. You see that is calling FIG, the tool, using high verbosity for you to see, light runs, which means we are going to do things fast for the demo. This has bad statistical properties, but we want to be fast now. And we are going to run simulations for 7 seconds. After 7 seconds, simulations stop, and they're going to show you a confidence interval, which is the probability of whatever you're asking. So let's start the demo with the tandem queue that we are just seeing. By the way, the tandem queue model in our language looks like this. You have Q1, Q2, and packages from here go here, okay? And we are going to study a transient property, the probability of having an overflow in the second queue before it empties, starting with one package, okay? So I can run this using crude Monte Carlo. FIG is going to run. for 7 seconds in simulations, and it's going to try and perform some confidence interval. Well, Monte Carlo didn't reach very far. Actually, it said, I didn't see any rare event here. Let's, instead of Monte Carlo, use rare event simulation. What is rare event simulation? I'm not going to tell you yet, because it can do it automatically for you, okay? And here, if you use just the standard configuration of figs, you already get a confidence interval for certain confidence that doesn't contain 0, so it's a useful thing. It tells you quite some information about the system. Now, of course, this is a toy example, it's even Markovian, so what the hell are we using rare event simulation and statistical model checking in general? Well, let's go just a little bit harder. We put another queue, and we allow probabilistic splitting, so packages from the first queue can be routed back, or they can go to the queue where I'm studying occupancy, or they can go essentially out of the system. And also, for the sake of argument here, let's do this server non-Markovian. Okay, we have a Weibull distribution here to analyze. The model in IOSA, so in our modeling language, looks like this. So in particular, here you have the probabilistic branches that you see here. This was added actually in this version of the tool, 1.3. And now we are going to do the same kind of tests, but for this new model, for cycle tandem Q. We're going to run Monte Carlo to see if it can converge to a value. It usually can. The problem with the values that it generates is that the confidence interval contains 0. So this interval is not very informative. It tells you, well, it is possible that there is no overflow at all, which is not very realistic. So let's try to use Fig to run the same as before, and Fig says, wait a minute, this model is too big. This model is very naively defined on purpose to show you that, well, the way that you could try to do just standard simulation, rare event simulation as before, is not going to work. So what can we do now? Well, the true value of Fig is that it can do rare event simulation compositionally. So instead of trying to build a full model of the system, it can build something called importance functions individually on each of these components, and then run rare event simulation as before, and give you a confidence interval which is much better than Monte Carlo. It is narrower, and in particular, it does not contain 0. Okay. Now, you can still argue that this is just a larger toy example, but a toy example in the end. Fair enough. Let's go larger. These are 7 nodes. The rerouting of packages from one node to the other is defined by this matrix. Arrival times are hyper-exponential, so they can arrive with different probabilities at different rates, and service times are weighable in this general fashion. Okay, so this is a considerably larger model. This is the IOSA definition of it. If you see, it has on the order of 500 lines, so it's already a larger thing. Well, as before, we are going to run Fig with Monte Carlo just to compare what can it do in the time it gives. Now we are studying a steady state probability. Let's see if Monte Carlo can find any rare event. It could not. Instead, if I use Fig with its standard configuration with this distributed compositional manner, we are going to see it converge to a value. Now, what you are seeing now is called a pre-processing. So it's finding the threshold, which is something that importance splitting needs. So this rare event simulation technique needs. And you could argue that, well, this is simulation time that you use and you didn't allow Monte Carlo. You're right. To compare with Monte Carlo, we should include this time into the larger run. We have done that. This is the demo. I'm not going to do it fast now. But in principle, to be fair, instead of giving 7 seconds to Monte Carlo, I should give 7 plus 11. Okay, so it converged, right? Fine. Final critique of all my examples here. They are all queuing systems. So is this a queuing tool? Aren't there better queue? Okay, fair enough. Yes, they are all queuing systems. The importance splitting, which is the main technique of Fig, the technique of Fig for rare event simulation is particularly good for queuing system, but it's not the only thing that it can do. We also have fault trees. Fault trees are models of failure for high reliability systems, where we can have failures defined in different ways. For instance, these are components, individual components. This gate, it's called here, tells me that if either of the elements fails, then I'm going to observe a failure. This is an OR gate. This is an AND gate. It tells me that all of the elements here have to fail at the same time to observe a failure. We can also have dynamic behavior. These are spare gates. So we have a primary component. If the primary fails, then we are going to resort to a spare, either of these two spares. And then we have observed no failure. But then if everything fails here, then we are going to observe a failure. And on top of that, we can add repairs. Okay, so every one of these components can fail and then get repaired. All of these with different distributions. So the failure time and the repair time can be described with non-Markovian distributions. So these are no longer just fault trees. These are dynamic repairable non-Markovian fault trees. And they can be large. Okay, this is hex, a very typical example from the literature. It has dynamic edges like this failure dependency and the spares that we were discussing, and we have different repairs. Now, this model is considerably large, so it's very difficult to write the IOSA model out of it. What we do instead is we define a language. This language is called Kepler because it was inspired in another language called Galileo, where you can just describe the structure of the tree. Here, very textually, you see that the top level is hex, and then we have an OR gate, which is the interface, and then we have something called a voting gate, which is the memory, etc. From this, we need to compute the IOSA model, that is the input of Fig, and for that we have created an interface called, doesn't matter how it's called, but we can give as input to this system the FT file that we have. We are going to create an IOSA file, and we are going to study unavailability of a steady state property, and I'm going to create an importance function. Notice that so far I just vaguely mentioned an importance function. So what is this thing? Well, an importance function is the core thing that you need to perform rare event simulation using importance splitting. So if you do that wrong, importance splitting is extremely bad. Rare event simulation is extremely bad. And we have been doing that without even mentioning what is an importance function, how do you compute it, etc. That's the core of the tool. Okay, you automate all of that, and that's completely general in terms of the model. You're not going to see what's going behind the scenes because that's what the tool is hiding for you. And it can adapt to different systems. Before we were seeing different queuing systems, now we are seeing a completely different system, a reliability system via fault trees. Okay, so it compiled the model. The model is actually this one that you see here, 1,000 lines more or less. And now I'm going to run as before. Do like this, big demo with hex. This guy.
But we are really running out of time. So
okay, sure. So let me just run this in the background. I just show the final thing, Marco. And what I'm going to do here is just pass this importance function that was computed from the tree. That's the point. Even though it looks as a large input, it was automatically generated, and as it runs, because it has to perform some computations for the pre-processing that we mentioned before, let me show you just if it wants to be shown, the main page of the tool where you can, it's freely available. This is GPLv3, it's written in C++. Compilation, instruction, installations are all there. That's why I didn't go through these things, because you can find them online. Of course, this runs in Linux. We have also made it run in Mac. There's no official support, but it runs. Don't even think about Windows. Sorry, Aaron. And yes, okay, this is just to show you the final output of the tool that it computed the value in that large system. Now I'm going to stop because I stole too much time. Apologies. If it's stopping, yes. And
okay. So thank you, Carlos, for the presentation, and sorry for being so quick.
For running over time.
Susanna would like to have a quick question, so please, Susanna, go ahead.
Just a question about your input language. It looks like CSL without nesting, is correct?
Similar. Well, the actual inspiration was Prism. You know the Prism model checker?
Yes.
It's the same kind of guarded model language, very, very, very similar, only that here we have clocks.
No, that's the language of the models, but the language of the properties.
Oh, yes, well, it's also the language of the properties of Prism, but for steady state, it is CSL, yes.
Okay, and so it's without nesting?
Yes, indeed.
Okay. Because I think nesting in simulation poses a certain number of problems.
We have not even considered the question, since what we are really grinding for here is this automation of rare events, right? So the kind of properties, they are useful in what you can describe, but we have never exploited that. We have transient steady state, and we are happy with that, essentially.